Hello, today I'm going to create a video, and I'll break this up to a series of videos to introduce the topic of dielectrophoresis. So this is just a introduction in terms of the general theory. There are definitely layers of complexity to this, but I just want to give a general overview so you know the terminology, you know what's going on, you know at least how to begin to apply this technique, or at least learn about this technique. And how I myself got into this was I started as a graduate student at Purdue, and my advisor at the time was interested in trapping and analyzing phytoplankton. So there was an individual phytoplankton that he wanted me to trap, but in suspension, and wanted to trap it so we could observe it. So let's just draw a microscope objective here to view what this particle is doing. But we want to hold it still. But he also did not want it against a surface. So we got rid of that. Now, so there was some magical force field, so it didn't want to come in with clamps. So there's some magical force to hold this in place. And after doing research, I thought, looking at these various techniques, dielectrophoresis may fit the bill. So ultimately, we have had a electrode configuration where this dielectrophoretic force is applied such that it would trap a particle and keep it suspended in the center of the channel. I'll show some preliminary results later from the study, but that's how I got into this, is trying to figure out how can we trap a particle. And dielectrophoresis is a good technique to perform separations as well as trapping. But that, in terms of the purpose of this talk, is just to familiarize yourself with dielectrophoresis, the applications, how you can integrate this with other microfluidic techniques. So we'll break this up into just the general introduction, some terms, some basic theory, and then the importance of the Clausius-Mossotti factor, classic electrode geometries that you'll see in literature, an introduction to numerical simulations. It's more straightforward than you think, including and then some recent configurations in terms of dielectrophoresis electrode configurations, and then applications including commercial products that are available, and then other considerations in other physics. So with this, we'll introduce dielectrophoresis and terminology, and it begins with electrokinetics. What is electrokinetics? Well, it's where you apply a field. In this case, we are focusing on lab-on-a-chip devices. And it's simple in that there's no moving parts. It's a straightforward application. You can use standard microfabrication established techniques to pattern metal. Now, the units of an electric field are volts per meter. And as you decrease that length scale, say for a standard voltage, so a volt, 10 volts, as you decrease that length scale into the micrometer regime, you can easily obtain electric fields on the order of 1,000,000 volts per meter. So, and of course there's variations depending on your geometries, but with that strength, you're able to manipulate particles on the micro scale that you are not able to, or at least not easily able to, on the macro scale. And because there's no moving parts and the fabrication is straightforward, you can incorporate it with other technologies. You can integrate it with other equipment, integrate it with the macro world in terms of interfacing with your fluid, your syringe pumps, interfacing it using like a card holder to make the electrical connections to attach to your waveform generator. So it's straightforward to apply this technique. Now we are focusing on AC techniques. You can do dielectrophoresis with DC currents, but usually when we talk about the theory and apply dielectrophoresis, it's a frequency dependent mechanism. And I'm going to focus on sinusoidal signals. I'm going to assume that when I talk, but you can apply square waves and pulses, etc. Just be mindful that when you apply these other non-sinusoidal waves, there are some frequency components within them that are beyond just what the amplitude is and what the phase is, what the period is of that particular signal. So there are some other frequency components associated with that. So sinusoidal is the cleanest signal that you can apply. We are also going to focus on in phase, meaning say 0 degrees and 180 degrees if you have two electrodes. That's what I refer to as in phase. Out of phase, you could have, say, 4 different electrodes of varying, just as an example, of varying phase within your system. But we'll briefly touch upon that later, but we are going to assume that we are using an in phase 180 degrees signal for our system. Now the techniques that we will focus on is obviously dielectrophoresis, but you can look up other terms including traveling wave dielectrophoresis, electrorotation, and electroorientation. Also, when you apply electric fields, you can also manipulate fluids. We will, at the very end, we will briefly introduce AC electroosmosis and electrothermal motion, mainly for the primary reason that when you apply an AC field, more than one mechanism occurs. Now you want to design your system appropriately so whatever mechanism you are trying to achieve will dominate over the other mechanisms. But that's where the design and understanding at least the scaling laws of these physics come into play. So once you have a good fundamental understanding of the physics that come into play, you can design your system appropriately, whether you want dielectrophoresis or other physics to complement your the goals of your device. So who cares? Why do we even think about dielectrophoresis? Why are people even interested in this? And there's different applications. You can assemble particles, you can do different things, but we'll put them under the umbrella of cell separation. And recent market report, or market analysis, valued the cell separation market, including centrifuge technique, etc., is around a little over $2 billion, increasing to almost $4 billion in the next 5 to 6 years. And this also includes not just centrifuge, but also flow cytometry. But this is where dielectrophoresis can come in and make an impact, in that you are sorting and manipulating particles based on their dielectric properties, as opposed to, say, fluorescent tagging or other techniques. So it complements other cell separation technologies. So the first thing, for those who are not familiar with dielectrophoresis, is that it is not electrophoresis. So in electrophoresis, you have a fixed net charge of a particle. So for electrophoresis, let's say you have a negative plate and a positive plate. So your positive particles will go towards that plate. Now that's electrophoresis. However, for dielectrophoresis, you need to have a non-uniform field. You also have an induced polarized particle that does not have a net charge. In some cases, you could have electrophoretic and dielectrophoretic cases, but we're just going to assume that it's a purely induced effect for at least the physics that we'll be introducing. So dielectrophoresis, you have an induced dipole, the net dipole within your system, and there is a non-uniform field. And in brief, we'll have some illustrations later, but in brief, you have your net, I'll draw this net dipole, and then the electric field on this side of the particle, the right side of the particle, is greater than the electric field, I'll say left side, right side, the electric field on the left side is weaker than that on the right side. So depending on the orientation of the dipole, the particle will either be attracted towards or repelled from the larger fields. And that's the essence of dielectrophoresis. But to get back to the main terms, you have an induced dipole and you have a non-uniform field. Those are the key characteristics you need for traditional dielectrophoretic manipulation. So a dipole itself, classic definition in terms of you have charges of the same magnitude separated by some distance. This gives you a dipole moment, is illustrated below. And there's some molecules that possess permanent dipoles, but we are going to focus on polarizable induced dipoles. So ultimately the force on the dipole does depend on the non-uniform, there's the del operator, electric field that is applied. You could also have a torque that is on a dipole that happens in terms of orientation. We won't focus our discussion on that. We want to focus more on a point dipole approximation in a non-uniform field, and that's the dielectrophoric equation namely takes into account that first equation on the slide. So that is the force on a dipole. And in terms of these induced dipoles, a particle undergoes polarization. So polarization is a material that contains charge which polarize under the influence of a field. The charges are bound, they move in opposite directions, and this is obviously frequency dependent because the ions have a certain mobility associated with them. And there's different polarization mechanisms and different mobilities associated with different fundamental mechanisms. So for example, electronic mechanisms, you have a negative electron cloud surrounding your positive nucleus, and when you apply your electric field, you have, for that instance, so let's say you have a positive, I'm going to exaggerate this. So here you have a net dipole based on this shift of the electron cloud. Now, there is a fundamental frequency associated with this to where if your mechanism goes extremely fast, your AC field goes extremely fast, it does not have time to react to your system. So for electronic mechanisms, yes, it's a high frequency. That polarization mechanism is usually there for your experiments. Now, coincidentally, interfacial polarization is what dielectrophoresis is traditionally associated with, and that relaxation, when you have the interface between two dissimilar materials, so say you have a particle and you have your liquid medium out here, there's an interface of two different materials and charge will build up at that interface. And then one may be more polarizable than the other, and then you'll have a net charge at that interface. And of course you have another charge, net charge, on the other side of that particle in terms of the alignment of its with the electric field. We'll have a better illustration later. But that relaxation occurs on the order of kilohertz to megahertz. So some traditional definitions: conductivity is a measure at which a charge can move through a material. Permittivity is associated with capacitance, or the measure of energy storage within the system. Here we're interested in interfaces. Polarizability, several definitions exist out there. I put two here. Is it how does that material respond to a field or produce a charge at an interface? And we're going to assume that all materials are not perfect dielectrics, are not ideal dielectrics, but are lossy dielectrics. So it is indeed a function of frequency. So let's say, just to put this polarization and the mobility of ions, just to give some illustrations, let's say that you have some electrodes, you have a dielectric medium, you have a dielectric particle, and then say at some instant in time there is a charge associated with these plates. You have your electric field, And then you have ions within the medium, ions within the particle that will respond. There will be shielding on the electrodes. The ions within the particle will respond as well. And then ions within the media will respond to the charges that were mobile within the particle itself. So you can imagine that there are two dipoles associated with this system. One that is associated with the particle, so I'll put a net negative and positive here just for the particle, and then the liquid is out here. But then you have to determine the net polarizability based on the interfaces of this whole system here itself. So what happens in terms of bringing conductivity and permittivity into this discussion? At low frequencies, the movement of free charge can keep pace, so conductivity dominates. At high frequencies, polarization or permittivity of the bound charges dominates. And then at some transition between these frequencies, dielectric dispersion occurs. So it transitions from a conductivity dominant regime to a permittivity dominant regime, or vice versa, depending on how you sweep your frequency. And for these approximations, for the equations that are used, a point dipole is typically assumed. It's valid if the sphere is small compared with the characteristic length of the field non-uniformity, so the electrode size or the electrode gap. So as long as your particle is small with respect to that, this assumption is usually fine. But if it's not, you need to incorporate higher order poles beyond the dipole. We will not get into that today, but that literature does exist and you can look that up. So here's an example of where a particle is more polarizable than the media. So say you have a metal particle, a very conductive particle within a low conductivity solution. You have your net dipole shown here. Now, when the particle is more polarizable than the media, positive dielectrophoresis occurs. Now, the dielectrophoretic mechanism is not shown here because this is a uniform field is shown, but if you have a more polarizable particle with respect to the media in a non-uniform field, you will have positive dielectrophoresis. On the next slide, we have where the media is more polarizable than the particle, and then notice that the net dipole has swapped. It's switched. So I'll go back to the previous slide. The particle is more polarizable. Dipole orients for this example, negative on the left, positive on the right. For this example, positive on the left, negative on the right. So you have a difference, and you can imagine that as you sweep the frequency, the dipole goes from one regime to the other. So for the positive dielectrophoresis, you see the positive and the negative, there would be an attraction here. So let's say, for example, this is a non-uniform field. The electric field on the right is greater. It would be attracted for that particular regime. Whereas here, if the electric field was greater on the right-hand side of the particle, you would have a net repulsion from this, and it would be repelled ultimately, this is a better arrow, repelled away from the stronger fields. So as you go to one frequency, it could be attractive, another frequency it could be repulsive. So this leads us to the Clausius-Mossotti factor and its importance. So we already talked about polarizability in the previous section, and now we can introduce the time average dielectrophoretic force with the following assumptions: a homogeneous particle, it's spherical, dipole approximation, and this is a in-phase field. If you deviate from any of these assumptions, corrections are out there, you can look them up, but this is a standard equation that is used just for some basic calculations and design methodologies. So you have the permittivity of the medium, you have the radius of the particles. This is proportional to the volume of the particle. So if you have a particle that is twice the size of another one, then that one's going to experience an 8 times greater force, assuming they're identical particles otherwise outside of their size. And then the term over here, you take your electric field magnitude, you then square it, and then you take the gradient of that, and that is your gradient of the field squared term. So the dielectrophoretic force is inherently significantly non-uniform for a lot of geometries, and we'll show an example of this when we do some introduction to numerical simulations later. So with that, all of these terms that I've gone over so far are positive, except now that deviation, that frequency-dependent variation, there is your Clausius-Mossotti factor. So the Clausius-Mossotti factor, the real part of the Clausius-Mossotti factor, is frequency-dependent. You have the complex permittivity of the particle and the complex permittivity of the media, which takes into account the conductivity, permittivity, and frequency of your system. The real part of that has for the assumptions provided here, has a range of +1 for positive dielectrophoresis, and then -1/2 for negative dielectrophoresis. So this is your range, depending on your maximum theoretical range, and is depending on the dielectric properties of your particle, your medium, and the frequency that's applied. So, hypothetical example, say we have a particle in a medium that's provided with these properties. And we'll focus on the red curve. The red curve is the real part of Clausius-Mossotti factor. The imaginary part is also shown, but that is used for out-of-phase components. So we're going to focus on the red line, which is the real part. And as mentioned earlier, when we talk about polarization, that at low frequencies, conductivity dominates, and that's illustrated here. And then at higher frequencies, permittivity dominates. And then the frequency in between, you have the dispersion from one mechanism, dominant mechanism, to the other. And then you have a crossover frequency. Here, the dielectrophoretic force is approximately 0. And a lot of researchers try to determine the crossover frequency. So they tune their media, because in most cases you can't tune the particle properties very well, or you're trying to determine the particle properties. You can't tune the permittivity of the liquid very well, but the conductivity, that's the most straightforward characteristic that you have control over experimentally. So you can tune the conductivity of your system, and maybe you have a system where the crossover frequency of a particle is shown with here, and let's say you have a second one. I'll just draw a crude. Maybe you have another one that does this. So let's say this is particle A and this is particle B, and if you apply a frequency, say here, so we'll say the frequency, I'll use AP for applied, well, particle A would experience positive dielectrophoresis and would be attracted towards your electrodes. And then particle B would experience negative dielectrophoresis and would be repelled from these regions. So you could essentially sort two different particles based on the behavior of the real part of its Clausius-Mossotti factor. We'll show some examples later. Now, if you don't have a homogeneous particle, if you don't have a spherical homogeneous particle, if you have a layered particle, there are models that exist out there, and this is what the Clausius-Mossotti factor would look like for those models. And there's some popular biological models that have been used. And in terms of those who are interested in cell biology and applications of cell biology, how does the Clausius-Mossotti factor change for these different particles? So let's say you increase the interior of the cell conductivity for whatever reason, it happens for whatever reason. That's the shift in the upper left of what would happen to the real part of the Clausius-Mossotti factor. If you increase the cell wall conductivity, I'm on the bottom left now, that is shown, or increasing the cell membrane conductivity, or increasing the medium conductivity. That's what these simulations show. So if you have cells of two different membrane conductivities after some reaction and you want to sort those, or based on their behavior, you can design your system accordingly, tuning the medium, etc., to get to the behavior, the separation characteristics that you want in order to properly apply dielectrophoresis for your system. So now we are going to go over some classic electrode geometries. And you will see several of these. One of the more popular, let's say probably one of the most popular in applications, is different variations of interdigitated electrodes. So think of comb-like structures where you alternate 0, 180, 0, 180 out of phase. Here we have a top view and a side view. Now, for positive dielectrophoresis, or actually for dielectrophoresis in general, recall that it's the gradient of the electric field squared. So you can imagine the electric field lines would probably look something like this between the electrodes. So where's the greatest non-uniformity as well as the greatest electric field strength? Well, of course, that's right there on the electrode edges. So if that's where the greatest dielectrophoretic force is, now we have to take into account the real part of the Clausius-Mossotti factor and whether it is attractive or repulsive. So the positive dielectrophoresis for the following slides, they will be illustrated with red particles, and for negative dielectrophoresis, they will be illustrated with blue particles. So for positive dielectrophoresis, they're attracted towards the field maximums and hence the electrode edges. Now you may experimentally also see pearl chaining. So if you have an electric field that's moving laterally for this illustration, you have an induced dipole and you have a neighboring particle that has an induced dipole. Well, you'll have an attractive force between them because the negative pole on one end will be attracted to the positive end of the other, and hence you will chain particles across your device in the direction of the field. So this is pearl chaining, and that happens with these particles when they are polarized. So this is an example of positive dielectrophoresis. So now what happens in negative dielectrophoresis? So negative dielectrophoresis, they're going to be repelled from these regions. And if you didn't have a lid, particles would just be floating, they'd be repelled, you wouldn't see them on the bottom surface. But if the gap between here is sufficiently close to where you put a cover slip or some insulative material on it, the particles will appear to be will migrate to the center of the electrodes, but on the opposite side of your device. So they're repelled, but they're repelled in lines. And again, if that lid is not there, they would just be freely repelled from the surface and suspending wherever they may be. So this is an example, some early experiments that I did to play around with this. The upper picture just shows no activity. Particles have settled down to the bottom. When I apply a large frequency 5 megahertz signal, the particles are aligned in the middle of the electrodes, but again, they are repelled. It's tough to determine that from this image, but they are repelled. They're repelled, pushed to the cover slip on the other side, away from the electrodes. And then positive dielectrophoresis, they are on the edges of the electrodes, and there are some pearl chaining mechanisms that occur as well. So these are just some experiments there. Interdigitated electrodes, you can commercially buy them if you don't have ways of fabricating them. They're a very popular geometry that is used. Another one, particularly for single cell experiments, is a quadrupole geometry. So imagine you have 0, 180 degrees out of phase as shown here. For positive dielectrophoresis, particles are attracted to the electrode edges. You may have pearl chaining. That makes sense. Now, negative dielectrophoresis, think about where the field is weakest. So, and this is a top view. We're assuming planar electrodes. So your electric fields would look something like this. So here's your field null. That's where the weakest point is. And yes, that's where you can trap particles, or where you would trap particles with negative dielectrophoresis. And this is a planar geometry. If you have two sets of them, you can stack them on top of each other if you want to trap a particle in suspension in the middle. You can do that with negative dielectrophoresis. So you can suspend particles. So I'm going to draw a side view similar to the illustration I had at the very beginning of this lecture series. So you can repel, and then you can have your suspended particle in the middle. So this is a quick example. We have, you can maybe barely see it, but our group milled with 100 micrometer end mill through just a circuit board, a printed circuit board, a copper-clad circuit board. We made a quadrupole geometry, and when I activate the video, the field is applied later in the video, but you will see some pearl chaining. You will see negative dielectrophoresis, and particles will be trapped at the center of the device once the field is applied. So that is negative dielectrophoresis. And if you go back and replay the video, you'll see some pearl chaining in the video as well. Okay, so these are castellated electrodes. So these are interdigitated, but they have, instead of these straight line features, they have these sort of square wave features that generate high gradients at the corners. Now, in some cases, you do have, some authors have shown where your two electrodes are aligned with each other as opposed to offset. So both exist. So you have your positive and negative 0, 180 is a better phrasing. 0, 180 degrees out of phase electrodes. You apply your electric field. Positive dielectrophoresis is shown here. Particles more likely to migrate to the corners. You may have pearl chaining. Negative dielectrophoresis, think about where the voids are. Think about where the nulls are in the system. And they're in those cavities. So these are for castellated electrodes. Here you have an example of sub-micrometer particles, fluorescent particles, that are trapped in both the quadrupole geometry as well as the castellated electrode geometry. So the top diagrams show negative dielectrophoresis for both quadrupole and castellated electrodes. And then the bottom, you have your positive dielectrophoresis at the edges of the electrodes. This leads into some numerical simulations. Now, this is an oversimplified analysis. So the potential of your field can be described as, or you can solve it using a Laplace equation. The electric field is the gradient of the potential. So you have your electric field. You then, recalling that we ultimately need to get to the magnitude of the electric field squared, and then you take the gradient of that. Because of that, it's extremely non-uniform to where you're going to need a high mesh within your numerical simulation to solve for the dielectrophoretic force. Because you're taking a gradient, you are squaring it, and then you're taking the gradient of that. So any errors from a coarse mesh are going to be amplified through your simulation. So a way of looking at this is, let's say you have electrodes, and we're assuming that there are no losses. Yes, there is shielding, frequency-dependent shielding on the electrodes depending on the materials. You can look up the details of that if that's important. But if you just look at the general design or order of magnitude approximation of what your dielectrophoretic force will be, this is a good start, and that's all we're going to cover here. So you have your, say, positive and negative 0 and 180 degrees out of phase potentials that are applied for, say, an interdigitated electrode system. If you want to study the boundaries of your system and the boundary effects, make sure that you have a healthy distance between your, assuming an insulative wall far downstream. You want to give it a nice healthy distance away from your electrode, because what these boundaries do otherwise is that they are insulative. So the electric field is obviously not going to bleed through those walls. It acts like a mirror, and you have the same geometry on the other side. So looking at this, there is a simplified way. If you were just looking at interdigitated electrodes, look for symmetry. So one way of symmetry is, say this is the middle of your device, you could cut it down the middle. Like, okay, you can simulate half of it, and that's fine, and that works. But think about what is the most simplified geometry that you could use for your system. For this example, this is what you would simulate. So the potential between two neighboring electrodes would be 0. Then you have a mirrored symmetry above the center of the electrode. So you can take this whole system, and if you want to look at the behavior of this system, you can just take this little sliver, analyze that, and get what you can from that. So in the end, look for symmetry within your system, because you will likely need a high mesh, even in 2 dimensions, to accurately model dielectrophoresis. So here's an example. This is not the whole simulation space. I zoomed in on a portion of the simulation space where you have 2 large electrodes with a 50 micrometer gap between them and 5 volts is applied. So this first figure shows the potential across it, going from 0 to 5, from black to white. Then you have your electric field magnitude is shown here. And then for your dielectrophoretic force, we are taking the electric field, we are squaring it, we are taking the gradient of the field squared, and you have this. And the color code is logarithmic, but if you convert it over, it's the scale shown at the top. So that is your magnitude of your gradient field squared. And as you can imagine, especially for this, this particular plot, the force on the electrodes is extremely high compared to that in the bulk. So if you have a particle out in the bulk versus a particle that is here, this one is likely not going to be manipulated, or it's not going to be manipulated as strongly as that is near the electrodes, because the field strength is just weak out there. So for example, just put some numbers to this. Let's say you have 10 micrometer particles. One of them is at a height, is resting on the surface, so its center is 5 micrometers above, so we'll say it's resting next to that electrode. You have another one that is one diameter off the surface, so a center to plate height of 15 micrometers, and another one that is 40 micrometers, so just a little over another diameter and a half away. How does the force scale? So we'll normalize it with respect to the one that is on the bottom, which is on the surface, so we'll call that the normalized one. The one that is 1 diameter away experiences a 10 times less force, and the one that's a further diameter and a half away is 100 times less force. So you can imagine any particles that are up here, how they are not impacted by the dielectrophoretic force. And because of that, there's some unique geometries that we'll go over in the next slides that try to look at this. So you can have electrodes on the top, you can have electrodes on the bottom, you can have three-dimensional electrodes, or different configurations that try to overcome this. But this is one of the things you need to be aware of with your dielectrophoretic system, that yes, you have to take into account the space, and you may need to optimize your system or design your system such that you can optimize your separation and distribute your dielectrophoretic force accordingly. So besides planar electrodes, which we've been focusing a lot within this lecture, we are going to look at some other unique dielectrophoretic configurations. And you can see some of these throughout some review articles, some well-written review articles by different authors. So one is making three-dimensional electrodes. And there are three traditional ways of doing so. One is extruding it with electroplated structures, so a microfabrication technique where you use a thick photoresist and you electroplate your metal extruded up off the surface. Another way is taking a thick photoresist and then going through a pyrolysis mechanism to where you generate carbon, so your structures will shrink, but the end result will be a carbon structure, a conductive carbon structure. And then you have deep reactive ion etched structures of a highly doped conductive silicon wafer. So those are the three primary methods of creating three-dimensional conductive structures. There's some other techniques as well, but these are the traditional ones. Another technique to make a three-dimensional distribution of your electric field is a technique called contactless dielectrophoresis. So you have your microchannel, which is illustrated in black, and you have these other channels that are filled with liquid, but the liquid, we will call these liquid electrodes. They are filled with a very salty medium, sometimes PBS is used, a salty liquid, and then your electrodes are applied. Let's say, for example, it's applied on these channels as well as on the other channels. But you apply it through that salty liquid. So your field, applying it over here, is applied through those liquid electrodes. And then because of that, you have your electric field propagating through the depth of your channel. So the height of these liquid electrodes are not planar anymore. The height of these liquid electrodes is the same depth as the main channel. Now the one thing that needs to be considered is this barrier. So this is fabricated traditionally out of PDMS, and that barrier is on the order, we'll say, of 20 micrometers. So that will act as an insulator to your electric field, so you have to ramp up the voltage that's applied. And then you may also have capacitive effects of that barrier, which will be a frequency-dependent impedance of your system. And there's been some designs around this, but just be aware of that barrier does impose some challenges in the design of your system. Insulator dielectrophoresis is a way of generating non-uniform fields using insulative structures as opposed to patterned microelectrodes. So, for example, with the illustration here, say you have your electric field that's applied, say, through the channel, and the electric field, as it comes through, constricts just like the fluid constricts here and then expands out. So you have your high gradients at the constrictions. And for this particular case that's shown in the illustration, you have negative dielectrophoresis. So particles that are focused and come in are ultimately repelled, at least the larger particles are repelled, because recall that the dielectrophoretic force is proportional to volume. So the larger particles are repelled from these regions and then ultimately will divert to another channel. Another example of insulative dielectrophoresis is using obstacles, either trapping or also sorting, separating based on these obstacles. So here you have glass posts that are microfabricated. And then you have constrictions. You can see the constriction and expansion of the field. And then in this case, using positive dielectrophoresis, particles are trapped at the constrictions where you have the higher non-uniform fields, the higher field magnitudes. They are trapped there, and then you can use this for your dielectrophoretic separations. Other techniques are trying to use virtual electrodes. So for this example, you have a field that is applied across an otherwise parallel plate system, which would be uniform. But there is a photoconductor that when you apply your illumination pattern, where it is illuminated is more conductive. So what is shown here is a series of negative dielectrophoretic traps where particles are trapped in the shadows, the dark areas, and then this light area is where it's more conductive. And from that, you can go to the journal article. It has some interesting videos showing this, and others have replicated this as well, is that the video shows like a conveyor belt of these dots, and you can move these particles left to right and in different directions. So you have this dynamic virtual electrodes that can be dynamically reconfigured within your system. Now, if you wanted to trap nanoparticles, recall that the dielectrophoretic force is proportional to the volume of the particle. So if you're trapping successfully maybe 1 micrometer particles, and you said, hey, I want to trap 100 nanometer particles, well, you have to increase your dielectrophoretic force for your system by 1,000 because of that. So one way of doing it is, yes, you can crank up the voltage. You can do that, but that is not extremely feasible for various applications. Usually bad things happen when you increase the voltage. You may also have limitations in terms of the amplifiers that are available for the frequencies that you want. Another way, again, you have the non-uniform fields to think about, is you can shrink your electrodes. You can shrink your electrodes. You can make them in 3 dimensions. And either combination of those, because there's people who've made nano electrodes, both in 2 dimensions, 3 dimensions. Here's one that was created by our group, where you have a sub-micrometer 3-dimensional nano needle that is coated with gold. And from that, you can trap nanoparticles. This is just one example of many where 3-dimensional or 2-dimensional nano electrodes can be fabricated. And from that video here, we've trapped smaller than this, but this is a nice highlighted video showing a trapping of positive dielectrophoresis followed by subsequent repulsion with negative dielectrophoresis at a higher frequency. And you also see some circulation, and we'll get into that as well. Another technique, which we won't go over, but we did in an earlier slide discuss the imaginary part of a Clausius-Mossotti factor. So if you have a traveling wave dielectrophoretic system, you need to take into account the imaginary component of the Clausius-Mossotti factor, and you can perform traveling wave dielectrophoresis. So say you want a particle to translate along with the field. First, it needs to be repelled from the electrodes. So you need to have negative dielectrophoresis. And then you need to have a non-zero imaginary part of the Clausius-Mossotti factor. And that will help with its translation. So hence, for this particular configuration, the properties of the particle in the medium, this is your region for traveling wave dielectrophoresis. And this has been used to selectively sort and trap particles. So a spiral configuration is a straightforward way of creating a traveling wave system in a planar single deposition, metal deposition application. So here we have two different cell types, one that has been infected, one that is uninfected. The uninfected ones experience positive dielectrophoresis and are trapped. The infected ones experience negative dielectrophoresis, and not only are they repelled, but they're directed by the traveling wave system to be concentrated in the middle. So now we're going to look at applications, including commercial products, and some we've glossed on in earlier slides, but separations is a primary application of dielectrophoresis. So here we have just one of many examples where they have an E. coli derivative that is stained to demonstrate the differences of live cell and dead cell behavior. And for their interdigitated electrodes at a lower frequency, 10 kilohertz, they all experience negative dielectrophoresis. At a higher frequency, they all experience positive dielectrophoresis, but at a sweet spot of 50 kilohertz for their example, the dead cells and the live cells experience different dielectrophoretic forces in terms of positive and negative, and hence can be sorted and monitored for their device. And then in the upper right, you see the electric field squared, not the gradient. You still have to take the gradient of that, but you can see that for different heights above your system, you have your decreasing square of the field, and you can imagine that after you take the spatial gradient of that your dielectric force would be significantly decreased as well away from the height of your system. Another way is, outside of sorting, is to translate particles. In this case, we're translating individual particles. So you have a strip of independently addressable electrodes on the top and on the bottom. So it's a three-dimensional arrangement of two planar electrode surfaces. You can independently address these electrodes and have a particle translate around to different portions within this. I use this for my earlier graduate studies and was able to manipulate a particle to different electrodes, and then also playing with trapping on the right particles that are continually being flowed, concentrated, released at different time points for trapping, manipulating one particle, many particles, controlled release, controlled direction, using dielectrophoresis. So here's some geometries, planar, that can manipulate. Typically these are designed for individual single particles, but not necessarily. So here is a exposed electrode in the middle with a electrode on the exposed ground electrode on the outside. And how it's oriented is you can have an array of traps, but this is a positive dielectrophoretic single cell trapping geometry. This point and plate system, you can imagine the electric field fanning out. So this is a positive dielectrophoretic trapping system. This is a octo pole arrangement of electrodes for a negative dielectrophoretic trapped particle in the center. And then this is also a negative dielectrophoretic trap of a particle, but on the surface in the void of the electric field. So you can imagine the electric field being applied across the strips and geometries here. So you can have different arrangements in terms of these particle manipulations. So we have electrodes on the top and bottom, which is illustrated here, of particles that would come in, be focused, analyzed, and then depending on the behavior would be sorted one way or the other. So with respect to sorting, if you have continuous flow, the particles can come in and then maybe larger particles go one way, other particles go another way. Maybe you have a frequency dependent system on, say, target A, target B, and your waste would be unaffected by your system or designed that way to where you have maybe a set of electrodes that are targeting target B and the set of electrodes are targeting A, and then you have some separations downstream. And that relates to a technique called field flow fractionation, where you have particles that experience a sedimentation force, a hydrodynamic lift, and then in this case, a repelled dielectrophoretic force. So you would have, say, two different particles here and here, and if they stay in this system for an extended period flowing downstream, they will reach a steady state height. And if you can monitor that height, you can characterize your particles based on the frequency that's applied or by the height, or you can sort them based on their height differential. And then others use some lateral field flow fractionation techniques as well. So at different points, the force is laterally applied, so you have your fluid flow coming in from left to right. And then based on how strong the repulsion is, some particles may be released here, some may be released there. There's different geometries. But this relates into our commercial products, which we'll get into now. So the first commercial application that we will talk about is ApoStream, where their focus is, yes, using field flow fractionation, but trapping tumor cells, and the normal cells are continuing to just flow downstream. So you have your positive dielectrophoresis that is trapping the tumor cells, and negative dielectrophoresis is repelling the normal cells away. So looking at different types of cells, they found that, okay, at a certain crossover frequency, which will apply for our system, the normal cells will experience negative dielectrophoresis, and then the cancer cells, circulating tumor cells, will experience positive dielectrophoresis and be trapped for our system. So it's a flow sorting system. The next system that's commercially available is called DEP array, where you provide a sample, the system will trap individual cells and put them on a coordinate gridded, independently addressable electrode array, and they're trapping them with negative dielectrophoresis within a potential cage, and then a confocal camera will come through and scan every single particle within the system and provide the user with a library of responses, of optical responses for everything that is trapped. And then the user decides whether to keep some particles or to remove other particles. So then the system will say, let's say for example, it does not want this particle. It will then independently address them to a waste, but then say it wants this particle, it will then take it over to a, we'll call it a keep, a portion where you keep it, and then it sorts them out individually based on what the user wants in terms of the response, the optical response after the confocal scan of the different fluorescent markers. A third one, called 3DEP, where you have 20 wells that have 20 different frequencies that are applied, and you put your cells in your system and say you don't have any knowledge or you desire knowledge of its Clausius-Mossotti factor, and at these discrete frequencies you can obtain this data and it can fit to it, and then maybe you alter your cells in some way and you can get a new change of your system and you can monitor it in this way. So what happens is you inject your sample of all your particles, and if the particles experience negative dielectrophoresis at a particular frequency, it'll be concentrated in the middle. Just picture your interdigitated electrodes that we went over earlier that are just wrapped around in a well. So this is a rather straightforward application of, with printed circuit board technology, you can have a layer of metal, a layer of insulator, a layer of insulator, a layer of metal, a layer of insulator. So you can have that in effect have a three-dimensional, quasi-three-dimensional configuration of interdigitated electrodes. And then you have your positive dielectrophoresis, where particles are attracted to the edges. So a camera can monitor light that is being shown through the device, and you can see how rapidly particles are attracted to the edges or repelled to the center. And from that, you can extract a Clausius-Mossotti factor of your particles. Another one by Panasonic, another commercial application, is a combination of dielectrophoresis with impedance spectroscopy. So there's bacteria floating in your system, they trap it using positive dielectrophoresis, and then use a impedance detection, impedance spectroscopy, to determine how many bacteria are present. And you correlate it with some known library, and it can determine the number of bacteria, the concentration of bacteria within your system. So a combination of dielectrophoresis to concentrate the sample, and then impedance spectroscopy to count and determine how many are present. Another application is used to size particles. So you have dielectrophoresis that will, similar to the previous device, concentrate particles. And then you have a laser that comes through. So this is where you're concentrating your particles. Laser will come through, and then for these small of particles, you will diffract light. And your optical detector will monitor the intensity of diffracted light. So for larger particles, when the dielectrophoretic force is deactivated, they will release. So over time, you can monitor the intensity of diffracted light with respect to time. The larger particles move away slower, smaller particles will diffuse away faster, and from that you can determine the size of the particle. So a combination, the dielectrophoresis is used to trap and concentrate the particles, but then it's deactivated and intensity of diffracted light is monitored to ultimately get your measurement. So dielectrophoresis uses a tool to concentrate, similar to the previous application. An emerging startup company, Biological Dynamics, is using a series of electrodes that are coated with a hydrogel in using whole blood. And the importance of this hydrogel and this coating that they use is to protect the electrodes, because whole blood is very conductive There you can also have some electrochemical effects on your electrodes depending on the electrode material that you use. But ultimately, they use this to trap nanoparticles, DNA from whole blood to stain and analyze later, and then remove the cells to do adequate visual analysis of what they captured. So besides dielectrophoresis, we're going to introduce some other physics because other electrokinetic mechanisms exist. It's just a matter of whether you account for them, whether you can design around them, or whether you want them for your system. So keep in mind, so far we're talking about dielectrophoresis, but the Clausius-Mossotti factor will change for non-spherical and inhomogeneous particles, shelled particles, and there's a lot of different geometries, both numerical and geometrical, that you can use. Just be mindful of those. We won't go over those, but just be aware. Your particles may orient in the direction of the field via torque, electroorientation. If you have access to higher megahertz frequencies, the orientation may change. So if you generally, the long axis aligns with the field. Sometimes it will align at higher frequencies. Orthogonal, the long axis orthogonal to the field. And that it's not extensively used, but that is a technique that can be used to characterize the dielectric properties of your particle, called electroorientation. As mentioned earlier, multipoles cannot be ignored, should not be ignored, if the particle size is on the order of the electrical characteristics, especially for single cell traps. Those need to be considered. Particles also interact with each other, Pearl chaining. We mentioned that earlier, so that may be a consideration for what you're trying to do. Electrorotation is a technique we do not talk about. Think of your quadrupole geometry, 0, 90, 180, 270, but now you're doing an out of phase component, and your particle will, depending on its frequency dependent, it'll rotate in one direction or the other at a certain rotational velocity, and you can extract the dielectric properties of the particles based on its rotational velocity response. So you can get dielectric spectroscopy of individual particles using this technique. There are challenges associated with that. We won't get into those, but that technique does exist. So when you apply an electric field to a system, you will heat it up. You will, the liquid itself has some conductivity. You could be using DI water for your preliminary experiments. Then you throw in a cell growth media and other things happen. There is the temperature is proportional to the conductivity that you use. So if you go from DI water to cell growth media, that's a very large swing in conductivity. You will get significant heating. And for that and other reasons, low conductivity solutions are typically used for media, cell growth media or cell testing media. So on the order of tens to maybe hundreds, low hundreds of millisiemens per meter. And when you do heat your fluid, what happens? Convection comes to mind. Hot air rises, people are familiar with that. But for microsystems, in general, convection is small compared to conduction. So if you have a relatively low heating, so below 10 degrees above ambient, and your restriction is on the order of 100 micrometers, these are just very round numbers, buoyancy forces, natural convection can be neglected, and you can focus on conduction if you want to do a heat transfer study of your system. But the electrical properties do change. So per degree change, there is a decrease in permittivity and an increase in conductivity. So if you have a fluid that has a gradient of permittivity and conductivity, and you apply an electric field across it, you will generate a body force, an electrothermal fluid body force, which is frequency dependent. You have a coulombic term, a frequency dependent term here, and your electrothermal motion will occur based on the gradient of temperature, so the non-uniformity of the temperature, the non-uniformity of those dielectrics, of your dielectric, and then with the electric field. So this is the equation that drives that. You can look up details of electrothermal motion. There's a lot of different articles out there that do that. But heating is proportional to the square of the applied field, as we showed earlier. And this body force is also proportional to the square of the electric field. So if you're experiencing electrothermal motion from Joule heating, from internal Joule heating, and you double your voltage, you're going to have a significant increase in electrothermal fluid motion. Whether you want that for your system, likely not. You take that into consideration. If you have external heating, like say optical heating, where your heating is independent of voltage, then your electrothermal motion is still proportional to the square of the voltage and the conductivity of the media. But in most cases, you're likely dealing with Joule heating from the field itself, and you have to be aware of the scaling of your electrothermal motion. Electroosmosis and electrophoresis, these are linear characteristics. If you apply an AC signal, you will not get electroosmosis, you will not get electrophoresis. But I bring this up in terms of just looking at the interaction between ions in a charged surface, because this leads into, and this is just a gloss introduction to AC electroosmosis, which is a phenomenon associated with induced charge electroosmosis. You can look up all these details. We can dedicate another topic to this extensively. You can read these bullet points on your own time, but the best way to describe the fundamentals of AC electroosmosis is by considering two electrodes that are polarized. You have ions within your media that interact with this. But first, the electric field has some curvature associated with it. It's non-uniform. And then the stronger field is towards the center. It will shield the field, but at least the ions are there. Now, when the ions are present in that location first, because it's stronger, they'll be attracted to that area first, you will have a tangential component of the field, which will then take the ions, slip them across the surface, dragging water molecules with it. You have interaction between that. Induced fluid slip on the electrode boundaries, and then at least for this configuration, you will get fluid flow here and here. And there's different configurations for AC electroosmotic pumps and mixers and different things. We'll go into that, but at least these are the physics that are involved, so at least when you observe some mechanisms, you may be familiar with what's going on. So at some point, at low frequencies, the ions will shield it. You won't get your fluid motion. At high frequencies, there's not enough time for the charge to accumulate on the surface, so it will decay at low frequencies and decrease at high frequencies. And again, this is just an introduction. You can read more on this. I just want to make you aware of other mechanisms that exist when you apply your field. So when you apply your field, yes, you want to have dielectrophoresis for your system, but you're going to heat your sample. You're going to have electrothermal flow. You may have AC electroosmosis, which it should be mentioned that this will decrease for greater conductivity of your media. But this will increase for greater conductivity of your media. So you have to play a balancing act there. But you also have Brownian motion, boiling, gravity, other forces to look at. So a good paper that I recommend looking at is just to sort of understand the scaling and the design and how you would go into it. This looks at some coplanar electrodes with a 25 micrometer gap between them. And they studied with all these different mechanisms if you have a certain particle size of a certain with an applied potential and a applied fluid conductivity, what's going to happen to your system. So they have a lot of figures, a lot of interesting things, but I just want to throw one from the paper here, where you have a sub-micrometer particle. What is the displacement of that particle from Brownian motion, from gravity, from dielectrophoresis for a certain conductivity media over a certain applied voltage? So here you may say, I want to trap my particle with dielectrophoresis, but for this particular geometry, you're going to have significant competing interactions with electrothermal flow, with electroosmosis if you're at lower frequencies. So just be aware that when you apply an AC field, more than one mechanism occurs. It's just a matter of design, whether proper media, proper electrode geometry, etc. Design your system appropriately so you can modify it to where you have your dominant mechanism that you want for your system. So with that, we'll conclude this talk, and I do recommend the following textbooks that are here. I use this to gather a lot of some information, but there's a plethora of journal articles out there as well. But if you have questions on these topics, feel free to contact me, and thank you for paying attention to this video.